thanks for the introduction, Michael. And yeah, thanks for having me here to talk to you about neutrinos. I saw a comment in the chat saying IceCube is so cool, and I definitely agree with that. And I hope to convince you all of that by the end of this talk. So I've titled this talk, Everything You Always Wanted to Know About Neutrinos, but were afraid to ask. And I've kind of structured it around a couple of basic questions and trying to start from the ground up and not assuming too much. So you can get a feel for, what is IceCube? Why is it built the way it is? What could we use it for? And what have we learned from IceCube so far? So the very first thing that you might want to be asking if you're interested in neutrinos is, what is a neutrino anyway? And here our story begins in the 1930s with the mystery of beta decay. So beta decay is the process by which particle physicists observed that neutrons could decay into a proton and an electron. And this is something they kind of understood in theory. And we know from particle physics, there are laws of energy and momentum conservation. You expect that the proton goes one way, the electron goes the other way, and everything forms a nice sort of balanced momentum conserving reaction. But actually, when particle physicists were observing this reaction, what they saw was something a bit more like this, that you would see the proton and the electron, but you would also be able to notice that there was some missing energy and momentum in this decay. And so what do you do when you have a problem where you expect two particles to come out, but it doesn't really look like a two-particle decay anymore? Well, that is where Wolfgang Pauli, the so-called postulator or godfather of the neutrino, comes in. And so he basically had this fantastic quote for how he approached the problem. I think it kind of tells us a lot about neutrinos. So he said, "I've done something very bad today because I've proposed that there is a particle that cannot be detected, and that's something no theorist should ever do." And I really think that this should color how we understand neutrinos. So he basically said the solution to this beta decay problem was to have a particle called the neutrino, neutrino being a little neutral one Italian word, which basically, describes a neutral particle. And so basically what Pauli was proposing is that there was a particle which was evading detection in detectors because it was electrically neutral. It interacted only via the weak force, one of the four fundamental forces of physics. The particle also had a very tiny cross-section, and it was massless. So all of the things that you might usually use to measure a particle would not work. And therefore, when you looked at it in a detector, basically you just see nothing because the particle that was being produced couldn't be detected. And so basically, if we go back to our idea of beta decay, the reason that energy and momentum wasn't being conserved is because some of the energy and momentum was being carried away by this invisible neutrino. Now, you might have heard in the popular press even neutrinos described as ghost particles, and this is basically why they got that name. And it kind of, there's an element of truth in it. It's just that they're basically passing through our detectors and you can't see them, and therefore it's difficult. You can only infer that they existed by virtue of their absence and how everything else behaves as if they were there. So, of course, it's not good enough in particle physics to come up with a nice sounding theory. You have to actually prove it. And so how could you go about proving that neutrinos really existed? Well, the idea was quite simple. So it was thought that basically the reaction could also go in reverse. So if you would take an electron neutrino, and if it would interact with a proton, you could turn a proton into a neutron and electron. And so the idea then is that you could basically detect the electron and neutron, and if you would suddenly see these protons sort of decaying into these two daughter particles, then you could basically infer the presence of the neutrino. And so the problem is you need a large number of neutrinos in order to make this happen. So where do you get neutrinos from? Well, this was the 1950s now, and it was the age of wonderful nuclear power. And so what scientists did is basically they built a tank full of protons very close to a nuclear reactor. And it was thought rightly that neutrinos would be produced in the nuclear reactor. And so basically when this tank was observed, you could clearly measure both the electron and the daughter neutron. And so, okay, that's cool. That tells you that protons can decay into electrons and neutrons. So does that mean you've solved the problem? Well, it's a little difficult to prove that actually the reason that the proton had this reaction is because of neutrinos. But there's an easy solution here. All you have to do is you switch off your nuclear reactor. And when you switch off your nuclear reactor, what you find is that the decay completely stops. And then you turn the reactor on again, and then they start decaying again. And then you turn the reactor off again, and then they stop decaying again. And so what that tells you, this reaction only happens in the proximity of an active nuclear reactor, and it only happens because the active nuclear reactor is producing the steady stream of neutrinos. And so this experiment was done and then published the first experimental evidence for the existence of a neutrino in 1956, and the Nobel Prize was awarded in 1995. And we've learned a little more about neutrinos since that time. So now we know that there's actually not one type of neutrinos, but three. So in particle physics, we have something called the standard model of particle physics, where you have different generations of particles. So you know that the electron is a negatively or positively charged particle with +1 electrical charge. And actually, there are two more versions of particles that are similar to the electron. That's the muon and the tau. And the muon is substantially heavier than the electron, but behaves otherwise pretty similarly. And the tau is substantially heavier than the muon and substantially heavier than the electron. Also has +1 electrical or -1 electrical charge, and also behaves similarly. So there are the three types of charged particle, and each one has an associated neutrino. And again, their properties are quite similar, although yeah, the mass can be different. And so in general, electron neutrinos are involved in interactions with electrons, muon neutrinos involved in interactions with muons, and tau neutrinos involved with interactions of taus. So now, why are astronomers interested in neutrinos at all? And here we start a century ago with Victor Hess. So here he is pictured in his famous balloon. So Victor Hess wanted to study the phenomenon of ionizing radiation that was measured in the Earth. So he did this around like 1912. And basically at the time, it was known that if you would take a sort of something like a Geiger counter and you'd measure ionizing radiation, what you find is that there was a lot of radiation, ionizing radiation on the surface of the Earth. And so obviously you want to know, where does this radiation come from? And what it was thought was that it was somehow coming from inside the Earth. So the Earth was producing all of this ionizing radiation, and you could measure that on the surface. And so, you know, Victor Hess had this great idea. I know what I'll do. I'll go in a balloon and I'll measure the radiation as I go higher and higher up in the atmosphere. And the further away I get from the surface of the Earth, the less radiation I will measure. And that sounds like a very straightforward idea, and it's really quite a good way of measuring such an effect. However, when he got in this balloon and he started measuring the level of ionizing radiation, he found exactly the opposite of what he was expecting. So what he found is that the higher up he went, the more radiation he would be measuring. And so that means that the entire theory of this radiation was completely wrong. It couldn't be coming from the Earth, because otherwise, why would there be more radiation in the atmosphere? And so actually, this led to the birth or first discovery of something called cosmic rays. So basically, what the results of his experiment showed is that there is a source of radiation that's outside the Earth. It's in the cosmos, and it's actually blocked by the atmosphere. So the higher up in the atmosphere you go, the less blocking there is, the more radiation there is. And so they were called cosmic rays, but actually this name is very misleading, because it was later figured out that the ionizing radiation was coming from charged particles instead. And so cosmic rays are actually not rays at all, but instead they are charged particles that are in space and collide with the surface of the Earth. So basically you have sort of something like this diagram on the left. You have protons or other charged particles bombarding the Earth from all directions. So that was 100 years ago in 1912. what do we know about cosmic rays today? Well, cosmic ray detectors have got a little bigger. So on the left, you can see a diagram of the Pierre Auger Observatory. This is the world's largest cosmic ray detector. So basically, I think this should give you a sense of the scale. It's sort of like maybe 60 kilometers by, I don't know, 50 or something. So, 60 by 50, it's several thousand square kilometers. It's absolutely gigantic. But in general, it's basically just detecting the same thing. So a cosmic ray comes in, it will have very high energy in this case, and then it causes a big air shower. So it interacts with the atmosphere and produces a lot of electromagnetic radiation, which is measured by the surface of the detector. And what have we learned from cosmic rays in the last century? Well, what we've learned is that they look something like this. So this is a plot that outlines the energy on the x-axis, and on the y-axis, the number of cosmic rays we measure at that energy. So it's in these kind of classic particle physicist units of electron volts. So basically at lower energies, so this is like 10 to the 9 electron volts, you have a very, very, very large number of cosmic rays. But most of them, we think, come from the sun. And so they don't travel very far to reach the Earth. However, as you start to go to higher and higher energies, then there's this regime where galactic influence dominates. And what that means is that we think that the sources of cosmic rays at, say, 10 to the 12 or 13 electron volts should be somewhere in our galaxy. And so then cosmic rays are basically coming from that area and then reach us at the Earth. And then beyond that, you have the extragalactic region where we think that the cosmic rays come from well beyond the Milky Way and actually come from very far away. And these sources have extremely high energy, or sorry, these cosmic rays have extremely high energy. I mean, just to give you a sense of scale, like the Large Hadron Collider Earth, that's the very best we can do in particle acceleration as humans, as puny humans. And we kind of would sit somewhere around here, like 10 to the 14 or 15, oh, sorry, 10 to the 14 electron volts. So the universe can do like 1 billion times better than we can. It's a big number, but that's the reality, that nature is just far more efficient at accelerating particles than us. And that's really interesting, because think how much work goes into engineering the Large Hadron Collider in this. It's something that's just happening naturally. And so that's basically the whole game of this field that was birthed by Victor Hess, is trying to unravel these cosmic ray accelerators, where they are and what they're like. So essentially, we might not know exactly what they are in all cases, but we know that there are places in the cosmos where particles go in with low energy, they get accelerated through some astrophysical process, and then they come out again. And when they come out, they're substantially faster. They have more energy. They've been accelerated. And so in this illustration here, you have a black hole and you have strong magnetic fields. And this is the sort of environment that is thought to produce particle acceleration. But there are many different places where this can be happening. In theory, at least, this is kind of there's a whole field of areas of there's a whole field of research where people are just trying to work out where might you be getting particle acceleration in the universe. So now, as an astronomer, I'm not really so interested in that, but rather I'm interested in knowing, on an experimental side, where are these sources coming from? What is the actual location where these particles are being accelerated? And so in this little diagram here, you can see you have the astrophysical source of a cosmic ray, and it is at a cosmological distance. So it's somewhere many, many, many megaparsecs away from Earth. And so it produces a cosmic ray. And so you think, okay, well, I just need to detect the cosmic ray and then work out where it came from on the sky, and then I can work out where the source of the cosmic ray is. But it's not that simple, because cosmic rays are, as I said, charged particles, and charged particles get deflected by magnetic fields. And the universe is absolutely chock full of magnetic fields. So actually what will happen is that when the cosmic ray is emitted, it will follow something like this red line. It will go in a kind of curvy, wavy route until it eventually collides with the Earth. And if it collides with the Earth and you can, measure that there was a cosmic ray that hit the Earth here, and you reconstruct with your hypothetical detector absolutely perfectly, you say, I know a cosmic ray arrived from that direction. Then basically someone will say, so what? That doesn't tell you anything about where the cosmic ray originated from, because if you would, go from the Earth and you'd extrapolate back to the point the cosmic ray interacted with the air shower and track back, extrapolate, you're not gonna find the source, because the cosmic ray didn't travel on a straight line. So it, just by looking at the same location in the sky, that won't tell you much. So this is why we go off for the theme, obviously, of the summer school with multi-messenger astronomy. So we think of other messengers that may accompany the protons or other cosmic rays and can tell us about these astrophysical processes. So I think as an astronomer, your default reaction is always, always, always to think of the photon. And if we're talking about cosmic rays of maybe 10 to the 15 electron volts, then you're talking about a photon of similar energies. And that would be known as a gamma ray. So that's the very, very highest energy type of photon we can detect. So why don't we just use gamma rays to identify sources of cosmic rays? Well, there's a couple of problems. I mean, gamma rays will be produced at astrophysical sources through the interaction of cosmic rays with ambient matter or photons. However, photons are firstly very easy to absorb. So if you have a photon that's traveling from your cosmic ray source, but it goes through some dust cloud, it's not going to reach the Earth. If it goes a little further and you're very lucky, then maybe it can collide with the Earth and you could detect it. Or in principle, it could also be detected by a space satellite. The problem, other than that photons get absorbed very easily, particularly at these energies, the universe is very opaque to photons. So photons can scatter off other photons from the CMB as well. So there's a lot of things to stop a gamma ray from arriving at the Earth. But even if you manage to detect them, you have a gamma ray telescope. Gamma rays can be produced in a lot of different ways. And so you can see something and say, okay, I'm pretty sure this is a source of gamma rays. But that doesn't mean that the source of gamma rays is also a source of cosmic rays. It might be, but it also might not be. So it's sort of a many-to-one problem. There's many different things that produce gamma rays, and you're only looking for a subset of these. However, as you may have guessed from the title of this talk, there is a third messenger option, and that is the trusty neutrino. So the neutrinos will also be produced through the interactions of cosmic rays with ambient matter and photons. And neutrinos, as we know, are electrically neutral, so they travel in straight lines as well. They also don't interact very much, so they will pass without any trouble through all the fields of dust that the universe wants to throw at them. And they are only produced from the interactions of cosmic rays. So if you can find a neutrino source, you can be damn sure that the source is also a cosmic accelerator. So by looking at this picture, it seems like the problem is very easy. All you need to do, you just need to build a neutrino telescope, and then you're able to solve this problem. Of course, just building a neutrino telescope is substantially more difficult than it sounds. So my next question to you is, what does a neutrino telescope look like? And if we go back to Pauli, he said that a neutrino is a particle that evades detection because it is electrically neutral. It interacts only via the weak force. It has a tiny cross section, and it's massless. So how might an experimentalist build a detector to detect such a neutrino? Well, if we would ask Francis Howson, the PI of IceCube, he might say something along the lines of, a neutrino telescope cannot study neutrinos directly because neutrinos are electrically neutral. So you have to actually detect things that come out of neutrino interactions. And if neutrinos have a very small cross-section, then the only solution is you need a very, very big detector in order to basically detect enough events that you even have like a handful, you have some decent statistics. And the other thing is that if you are trying to detect charged particles in a large volume, you cannot instrument the whole volume completely. So what you need to rely on is a detector where you have spaced out detector modules with gaps in between. And so the only way you're going to be able to detect particles that go through the gaps is if the medium of the detector is transparent. And if it's transparent, then when a charged particle goes through your medium and emits photons, the photons will be able to travel some distance and then be detected in the end by your detector. And that brings me to the IceCube Neutrino Observatory, which is shown here and fits the bill and basically is the world's largest neutrino telescope. So IceCube is at the geographic South Pole in Antarctica, so it is indeed very cool. And basically what was done, you go to the surface of the ice and then you drill down 2.5 kilometers nearly to the Antarctic bedrock. You lower a string into this hole and you fill the hole up with water and it refreezes. And on the string, what you have is 1.5 kilometers of just cabling. And then on the lowest 1 kilometer, you have photomultiplier tubes that are spaced along the length of the string. So a photomultiplier is just literally a photon detector. So a photon hits a PMT, as they're called, and then the PMT registers an electric signal to say, oh, there was a photon here. And so you do that not just once, but then instead of one string, you have this grid of 86 strings. And when you do that, you end up with an instrumented volume of basically nearly exactly 1 kilometer by 1 kilometer by 1 kilometer. So IceCube is 1 cubic kilometer of a neutrino detector. It is truly gigantic. This little smudge here is supposed to represent the Eiffel Tower, and that just gives you a sense of really how gigantic this particle detector is. So yeah, that's IceCube. It has in total 5,160 PMTs, and it was completed construction in 2013. So that was, 2011. So that's 11 years ago. So we've had 11 years of full IceCube data. So how does IceCube actually detect a neutrino? Well, as we said, we have a neutrino, in this case, not an electron neutrino, but a muon neutrino. That is traveling through the Earth because, like I said, neutrinos can travel through almost anything most of the time. And so this neutrino is traveling through the ice, but then it just happens to collide with one of the molecules in the ice, and there's a particle interaction. And then the neutrino produces a muon. And then this muon will travel several kilometers through ice before it stops. The muon is a charged particle, so it will be emitting light all the way through. And then if you're lucky, this muon will traverse your 1 cubic kilometer IceCube detector. And if it does that, then you'll be able to measure it. And so this is the sort of thing that IceCube would see. So IceCube measures light. In this diagram here, basically the detections are these little balls of color, and they're color coded. So red is early light and blue is late light. And you can really see, you detect early light here, and then you detect green light in the middle, and then at the end it's blue and it's near the other side. And I think you can imagine maybe visually, if you have this distribution of light, you could try and fit a line to it through some algorithm or a neural network or something, and basically estimate the trajectory of the muon through the ice. And that's exactly what IceCube does. So it basically tries to fit a line to this pattern of light deposition across time and space, and then is able to reconstruct the trajectory of the muon to within a few square degrees on the sky. And because the neutrino produces the muon, you can also work out then where the neutrino was coming from on the sky. The other nice thing is that the amount of light that's emitted by a charged particle in ice is proportional to the energy of the particle. So if a muon has high energy, it might look like this. If it has very high energy, then you'll get more light deposited at each of the individual detector modules, and you'll be able to measure that too. So just by looking at the distribution of light in our detector, you're able to figure out roughly how much energy the neutrino had. And that's a really important tool as well. So if you look at this distribution of what kind of events does IceCube detect as a function of energy, so on the y-axis here, you have the number of neutrinos, neutrino-like events detected, and on the x-axis, you have the estimated energy based on this property of how much light is deposited in the detector, then you get something that looks a little like this. So you have very, very, very many events around 1 TeV. This is 10 to the 12 electron volts. So GeV is 10 to the 9, so 10 to the 3, 10 to the 9, 10 to the 12. And then it sort of declines and it goes down. And then this is like 1 PeV. So this is 10 to the 15. And so what you can see is that actually it doesn't just follow a straight decline, but you have this kind of high energy excess, and it's a little hard to do just by eye, but I think if I plot it like this, it maybe becomes more apparent. Actually, the IceCube neutrinos, like the spectrum that's measured by IceCube, is that there's two distinct components. There's two different lines that kind of IceCube measures a superposition of the two. So why are there two different components in the neutrino spectrum? Well, as I said, what we really want is we want an astrophysical source at a very great distance to produce cosmic rays, and then those cosmic rays to interact at the source and then produce neutrinos, and those neutrinos travel all the way to Earth, and then they get detected by IceCube. And if we do that, and then we look at the direction the neutrino came from, we're able to say, there's a neutrino source and a cosmic ray source exactly at that position. However, as we already learned, the universe has lots of cosmic rays, and the cosmic rays are bombarding the atmosphere. And when the cosmic ray hits the atmosphere, that can also produce neutrinos. So these are not at an astrophysical distance, but they're neutrinos produced through interactions with the atmosphere. But they're still neutrinos. I mean, a neutrino is a neutrino. These two particles will be identical particles. There is no functional difference between them. And that's really a problem, because basically, when you look at the spectrum, what you have is in purple here now, you have the atmospheric neutrinos, and in red, you have the astrophysical neutrinos. And you cannot, on an event by event basis, say this one is astrophysical or that one is atmospheric. You can just say that there are two components, and they have different energy spectra, so they look a little different, but only in aggregate. So there's two groups of neutrinos, but the neutrinos themselves are identical. So maybe with that in mind, the next question is, what is neutrino astronomy? How do you do astronomy with neutrinos? And I think when you go back to this plot, this really kind of sets the tone for the entire field. So if you just look at it, you look at 1 TeV, you see nearly 10 to the 5 atmospheric neutrinos, and you see maybe 100 astrophysical neutrinos. So the key observation is that atmospheric neutrinos vastly, 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 vastly outnumber astrophysical neutrinos. And so basically, how I would describe neutrino astronomy is literally just the process by which you try and separate astrophysical neutrinos from atmospheric neutrinos. That's it. That's the whole game. That's the whole challenge, is trying to get these two groups of these two sources of neutrinos and try and separate them, because the neutrinos themselves look identical. So you need to do it only in a sort of statistical sense, and that's difficult but not impossible to do. And that's the main aim of neutrino astronomy. So how might we go about separating astrophysical neutrinos from atmospheric neutrinos? Well, as I mentioned, atmospheric neutrinos tend to have low energies. That's one thing we know about them. The other thing is that the cosmic rays that are producing atmospheric neutrinos are hitting the Earth from all directions on the sky, approximately isotropically. And that means that the atmospheric neutrinos are also going to be approximately isotropic across the sky. The other thing is that the cosmic ray flux that hits the Earth does not vary much in time. And so the flux of atmospheric neutrinos is also going to be roughly constant in time. So you measure, I don't know, one atmospheric neutrino every 5 minutes, and you measure it today, and then you measure it in 3 hours, and then you measure it in 3 years or 3 weeks, and you're always going to measure almost exactly the same level of flux. And that's actually quite a distinct property. And if we compare that, what do we know about astrophysical neutrinos? So we know that astrophysical neutrinos, unlike atmospheric neutrinos, tend to have higher energies. Also, if you just think of the night sky, so you've got this flux of photons, and the night sky is not a uniform gray color. It's black, and then you have a few particular bright sources like stars. You look up in the sky and you see dots, and then you see dark bits. And that's because the photon sky is not isotropic at all. It's very anisotropic. You have individual sources, and all the photons are clustered together around these individual sources. And neutrinos are going to be exactly the same. So you'll have different sources of neutrinos on the sky, and the neutrinos will be clumpy. There will be a neutrino source over there, and there'll be some astrophysical neutrinos from that source over there. And then over there, there'll be another one. And again, there'll be a cluster of neutrinos around that individual source. The other thing is that neutrinos might, I'd emphasize might, be clustered in time, because the astrophysical processes, these are natural processes, they're not necessarily uniform. They could be, but often they're not. So you can imagine you have a distant source that's not very active, it's not doing very much. And then suddenly there is some change in the cosmic ray / neutrino source. And so the source suddenly becomes active, it emits a lot of photons, and also it starts emitting neutrinos. And then the process sort of ends and the source switches off and the neutrino emission stops as well. And so instead of having this steady atmospheric neutrino flux, with astrophysical neutrinos, they might be quite grouped in time. I mean, it could be, it could be 100 seconds, it could be a month, it could be a week, it could be a day. But we know that the universe varies on all of these timescales. And if the sources of neutrinos vary on timescales that are on hundreds of years, then we might be able to measure the differences in the neutrino flux over time, that there might be bursts of astrophysical neutrinos. And again, remember, the atmospheric neutrinos are not like this at all. They're just going to be steady. So that's basically our two ledgers. And all neutrino astronomy relies on one or the combination of these three factors. So you basically look at the energies of the events, their spatial distribution, and their temporal distribution. And this is, the only three things you ever measure in particle physics, astronomy, whatever. It's always the same problem. So these are the things we have, the tools we have to try and distinguish atmospheric from astrophysical. How do you actually do it in practice? So neutrino astronomy basically relies on three distinct techniques, and they're actually quite simple if you kind of peel back all the layers and say, what are you fundamentally doing? So the first approach is to just say, I don't care about anything else in the universe. I'm just going to look at neutrino data from my neutrino telescope. And what I want to see is if neutrinos are clustered with other neutrinos, because we expect astrophysical neutrinos to be clustered. So you look and see, is my neutrino data roughly uniform across the sky, or is it very clustered in a couple of sources? And if so, then you can say, oh, well, then, these are probably sources of neutrinos. The other thing, step two, is that you say, okay, actually, I'm not going to just disregard the entire universe, but actually we know a lot about the universe, and maybe I have a good idea of where neutrinos might be coming from. And I'm going to leverage all of this astrophysical knowledge that we've got from other messengers, from photons of all wavelengths, and I'm going to use that to try and work out where neutrinos come from. And the other avenue is you kind of flip point two on its head, and you say, instead, I'm going to look at a neutrino that is very high energy, and this neutrino is probably astrophysical. And so let's take it as read that this neutrino is astrophysical. Can you try and find me the possible source of that neutrino based on the neutrino information? You look through electromagnetic or other messenger data to try and identify where the neutrino may have come from. So that is a very extended introduction. And now maybe to come to the actual, what I would consider the actual astrophysics, like what have we learned from all of the astrophysical neutrinos, which IceCube is so wonderfully able to detect. So let's go back to track one. Are neutrinos clustered with other neutrinos? So I have here on the left a sky map. So this is basically data from the IceCube Neutrino Observatory looking for spatial and temporal clustering within 10 years of data. So this, maybe you want to take a minute to think about this. This is what the sky looks like in neutrinos. And it's kind of color coded. So white is there's no evidence of neutrino emission at all, and kind of bluer is brighter. And then the hottest spots in the northern and southern sky are circled here and here. And to the untrained eye, or to the trained eye, I mean to my eye as well, this looks heavily anisotropic, right? You think like, oh, there's loads of structure there. There's loads of things that are probably neutrino sources, because it's really not uniform, and we expect atmospheric backgrounds to be uniform. However, it's not actually true. I mean, you expect that the atmospheric flux of neutrinos is uniform. However, when you have a uniform flux, you also expect that you would have some random fluctuations in the measurement of neutrinos from that flux. And that's, that's normal, that's well understood. And so what you do is you firstly say, imagine that I just had an isotropic flux of neutrinos, but then there was this random noise process that went on. Would the map look like this? Or is the map very anisotropic, much more so than you'd expect from random fluctuations? And IceCube has done this experiment. All of the IceCube analyses kind of revolve around this kind of process. And what they find is that the sky is consistent with random fluctuations from an isotropic sky. So basically, IceCube data alone is not able to identify any likely neutrino sources. So there are definitely astrophysical neutrinos in this sky map, but they're not clustered enough that we can detect them. So even though they're there, we can't identify where the sources of the neutrinos are just from neutrino data alone. But that's okay, because we don't need to rely just on IceCube. We actually know, quite a lot about the universe. So there are other avenues. So the second track is to try and look and see if neutrinos are clustered close to astrophysical populations. And just as an example, you could look at the sky map of gamma ray photons from the Fermi-like Gamma Ray Observatory. So if you look at the sky in photons with Fermi-like, you see something that looks like this, and you have the galactic plane here is very bright, that's the Milky Way. But then you have a lot of other sources, and these are all sort of circled here. So you see, like, the gamma ray sky is not very isotropic. You have particular points in the sky where you have sources. And so you take a map like this, but it could really be any wavelength at all, or any catalog of known sources, and you say, is this correlated with neutrino fluctuations? And this has been done a lot by IceCube, really many times. And almost all of the time, the answer is there's no correlation. But if I would tell you that, that would be a very boring sort of lesson to give. So I'm going to disregard all of the times, but there were many you should know where IceCube did not find anything. And I'm going to talk only about the times where they did find some evidence of a correlation, because that is the most interesting in my opinion. So the first thing was, again, going off this data from Fermi-Lab, there was a catalog that was identified based on that, and data from other gamma ray telescopes, which was derived. And the catalog basically said, let's look at the energy spectrum of all of these sources and see which ones seem to be the most promising that could be possible neutrino emitters. And the catalog wasn't very wrong. I think it was maybe like of order 100 sources or less. So it's just 100 particular points in the sky, and sort of the IceCube analysis said, let's look for neutrinos from these positions. And one of the sources was this beautiful starburst galaxy you see on the left called NGC 1068, a very nearby galaxy. And what was found is that actually this galaxy was in the same position as the hottest point in the neutrino sky from the map I showed you earlier. So the hottest spot in the sky was not significant on its own, because there's always going to be a hottest spot in the sky, and you compare the hottest spot in the sky to, if you search the whole neutrino sky and find the most significant point, and then compare that to if you have an isotropic distribution and look for the hottest point. And so basically, that in itself was not particularly significant. But if you are really just saying, I have 100 points in the sky, let me see if there's anything interesting, then you have a lot less, you expect a lot lower signal by accident. And so what this means is that actually the same data on its own is not significant enough. But when you combine it with astrophysical information, we can say actually it's rather unlikely to have such a strong correlation with a nearby galaxy by chance. And actually, when we say by chance, we mean something like at this 3 sigma level, to use these particle physicist units of 3 sigma or 5 sigma. And they basically just quantified the probability. So 3 sigma is sort of like 1 in a 1,000, maybe somewhere around there. So anyway, that's really exciting. And we can actually do more. I mean, now we have all of these neutrinos, we can go back and we can look and try and understand the properties of the neutrinos. And so if you try and derive the neutrino energy spectrum, you get something that looks like this in green. So this is the best fit muon neutrino energy distribution that's measured by IceCube. And you can see it's around 1 TeV. It goes a little below to a little bit above. And then this is a busy plot, but let me just walk you through the most important things. So this blue line and these black lines, these are upper limits from photon detectors, so from gamma ray observatories. And what you can see is that the neutrino flux is like 100 times higher than the upper limit on the photon flux. So really, really bright in neutrinos and comparatively dim in photons. And that might sound puzzling. I mean, that is a little bit weird. However, what we learned before is that neutrinos are able to travel basically unhindered. And so if there's dust or anything in the source of the, in like NGC 1068, the neutrinos will be able to get out, but the photons will not. And so that's actually what you're seeing in this plot. If this is indeed a neutrino source, then what you're learning is that the neutrino flux is really substantially brighter than the photon flux because most of the photons get hidden. And so it sounds a bit stupid, but it's like if you're, you break your arm and you go to the doctor and he gives you an X-ray, and the X-ray is able to show you what your bones look like, even though your bones are inside your arm and your arm is opaque. And that's exactly what you're doing. It's the same idea. You're sort of X-raying this distant galaxy with neutrinos, and the neutrinos are trying to tell you about what's going on inside the galaxy, but the photons can't go through the galaxy. So we can only see from the surface. And that's really exciting. So this is kind of the principle of neutrino astronomy in action, that neutrinos can be used to measure things in areas of space that we can't see by any other means. The other thing is that there was a search done by not just one of these galaxies that was similar to NGC 1068, but really 10,000 or more. And these galaxies were selected by their UV or infrared properties, or X-ray properties, sorry. And basically a search was done for correlations between these 10,000 active galaxies. So active galaxy just means all galaxies have a black hole at their center. And some of them are active. And when that means that they're active, it means that they're actively accreting. So things are falling onto the black hole. And when you have accretion, you can get an accretion disk, and you can have a lot of photons emitted, and generally you can have particle acceleration. And so this is kind of the thing that you're trying to trace and see if that's correlated to neutrinos. And what was found was, again, a sort of 3 sigma-ish correlation, and that's shown on the plot on the right here. So basically in black and in gray, you have different measurements of the IceCube neutrino spectrum. This is the full all astrophysical neutrinos. And then in blue, you have some estimate for the neutrino emission from these active galaxies. And what you can see is it's like very large and actually even overshooting at high energies. Of course, there's a lot of uncertainty involved at extrapolating from even 10,000 active galaxies. You measure the neutrino flux from the 10,000, and then you say, okay, well then now I need to account for the other active galaxies in the universe that weren't in my catalog, and that's a difficult calculation to do. But I think the general principle here is that there is a lot of neutrino flux that might be coming from these active galaxies, consistent with all of them at the highest energies. I want to say this is a very, very recent result. So it's just on arXiv. It appeared at the end of last year. It's still not published yet. So yeah, this is really hot off the press as a sort of as a sort of result. So basically, NGC 1068 and some other galaxies are likely sources of some IceCube neutrinos. And now you're probably wondering, why am I trying to talk to you about particle physics in the ZTF Summer School? I've gone on and on and on and on and on about all of these IceCube specific things. And you think, you know, where do astronomers fit in? Where is ZTF fitting into this picture? And so that brings me to track 3. The process by which you try and look for astrophysical sources clustered near neutrinos. And so to go back to this plot, again, we learned that high energy neutrinos are much more likely to be astrophysical than atmospheric. And so what IceCube does is it says, let's look at these high energy neutrinos and let's issue public neutrino alerts. So the basic idea is, again, that you have these neutrinos being detected by IceCube, and now IceCube has automated algorithms that run all the time at the South Pole to detect the neutrino and identify that it's been found. And when a neutrino is found, then they distribute the location, they transfer the data via satellite, and they give astronomers all around the world within, let's say, a couple of minutes, and then more information within a couple of hours to say there was a neutrino and the neutrino came from this point in the sky, and the neutrino is this likely to be astrophysical, and basically say, you know, astronomers, please point your telescopes to this location and tell us if there was anything interesting there. Actually, this happens a lot. So IceCube had an event selection, and they then changed it to produce even more alerts. And now with the second, in orange, the newest alert selection, we're averaging 1 neutrino alert every 2 weeks. So we've had already, way more than 60, and this was as of July, and that's nearly a year ago, or that is a year ago. So you can kind of easily imagine we've had another 25 since then. So basically, there are so many neutrino alerts now, we're literally drowning in them. And that's really exciting because we're moving to this regime where we can start to be finding interesting things. So yeah, what have neutrino alerts taught us? So firstly, I should say, what are we looking for? Like, where might neutrinos be coming from? Because you can't just look blindly for anything in the sky. I mean, if you look in any square degree of sky, there will be so many galaxies and so many, or stars or whatever. So you really have to narrow it down. And the way we do this generally is we talk to theorists, and theorists will consider all of the different astrophysical populations that we know about. And they'll say, oh, I think this might have the conditions to produce neutrinos, or I think this does not have the conditions to produce neutrinos. And so I think this kind of plot summarizes mostly what we're interested in. So you have gamma ray bursts, you have supernova with choked jets. So these are supernova where you almost had a gamma ray burst, but the gamma ray burst gets stuck in the outer levels of the star. You also have supernova with CSM interaction. So CSM is circumstellar material. So you have a supernova and you have a shell of matter around the supernova. And so the supernova shock comes out and then it collides with this shell of material that was lying at some distance around the supernova. Another option is active galactic nuclei, active galaxies, as I mentioned before, and most particularly blazars. So that's when you have a relativistic jet launched by an active galactic nuclei, and the jet happens to point towards Earth. If it points towards Earth, we call it a blazar. And the other thing is tidal disruption events. So this is where a star falls into a supermassive black hole. So this is just an overview, but these are basically 5 different populations we know about, and we knew about them independently of neutrinos. And when we do neutrino follow-up, we're basically trying to work out whether we find one of these things coincident with the neutrino, and if so, then we can kind of make a case that that thing might have been the source of the neutrino. So did we find anything interesting? Well, actually, the neutrino real-time alert program started, as you can see, in 2016. And within 1 year, there was already a very exciting discovery of IceCube 170922A. So all neutrinos are named after the date they're found. So this was found on the 22nd of September 2017. And so what was exciting about IC 170922A? Well, basically, when you looked at the position of the neutrino on the sky, what you found is that there was a bright gamma ray source. And actually, more than that, when you look at the bright gamma ray source, and you look at the light curve, so this was noticed almost immediately. This is the gamma ray light curve of the source in question. And so what you see is that basically this is where the neutrino arrived, and it was at the time when the source was undergoing an extraordinary flare, the brightest in its history. And that was really exciting. And so I think this is kind of my favorite summary of the idea. It's the New York Times headline: "It came from a black hole and landed in Antarctica. The first time astronomers followed cosmic neutrinos into the fire-spitting heart of a supermassive black hole." And yeah, this also was published in Science, described as neutrinos from a blazar. So what is a blazar? Well, again, it's basically just a type of active galaxy. You have the black hole in the middle, you have an accretion disk, you have very strong magnetic fields, and through that process, a lot of the matter is accreted onto the black hole, but some of it gets accelerated in a so-called relativistic jet. So you have particles streaming out at relativistic energies. And that's the idea. And then it's just a purely orientation-based definition. This jet happens to point towards us. Observationally, it looks very different than looking at it side on. And when it looks directly at us, then we call that blazar. So basically, this is what we think blazars are doing. It's really exciting. We have relativistic jets, we have shocks, we have acceleration, we have protons, and the protons eventually have interactions, just like I showed in my diagram before. The interactions eventually produce neutrinos, and those neutrinos can make it to Antarctica, where they can be detected by IceCube. So how does ZTF fit into the search for neutrino sources? Well, we have the ZTF neutrino follow-up program. So what we do, we have the neutrino direction and time, and ZTF is detecting 500,000 objects per night. And we put it into our magic black box called our neutrino follow-up program pipeline. And at the end, we hope to find a possible optical counterpart to a neutrino. And this is illustrated as looking very mysterious, but of course, you're now all seasoned veterans of the ZTF Summer School. And so you should know that this is actually not so complicated at all. So what we do in this step, we just try and reject stars and asteroids and planets. And we also require spatial and temporal coincidence. So we only look for things that are coincident with the localization of the neutrino, which is a few square degrees, and that are detected after the neutrino is detected. And then we usually only have a few remaining objects. And of these, we try and spectroscopically classify them. And then we hope to find the counterpart. And so if you're interested in this step, good, because in the next session, you're going to build your own neutrino follow-up pipeline in the notebook session. So we're going to come back to that, bear this slide in mind. So some statistics, basically we observe one neutrino per 5 weeks, something like that. And remember, IceCube gives one neutrino alert every 2 weeks, so we get about 40% of them. A lot of the time they're too close to the sun, or they're attracted, or for various other reasons we don't follow them up. So then the big question, what did we find? Well, so we found a tidal disruption event coincident with a high energy neutrino. This was published just in May 2021. And so it made the cover of Nature Astronomy. What is a tidal disruption event? Well, just to go into a little more detail. So you have, again, a black hole here, a supermassive black hole at the center of a galaxy. In panel 1, you see you have a star. The star approaches the black hole on a parabolic orbit. We all learned in school that the force of gravity is proportional to 1 over r squared. And what that means is that the star is distorted by tidal forces. And so basically the front of the star is being pulled by the gravity of the black hole a little bit more strongly than the back of the star. So the star is experiencing this net tidal force. And the closer the star gets to the black hole, the more extreme this tidal force becomes. It becomes stretched and stretched and stretched. And then at some point, this force exceeds the self-gravity that's holding the star together. And at that point, as you see in panel 3, you have disintegration. The star disintegrates, it falls apart. And then in step 4, you have all of this stellar debris. You've just shredded a star. It's really messy. And you have a black hole that's kind of providing the source of gravity. So generally, the stellar debris will eventually form an accretion disk. It will circularize and it will become very hot. It will emit a lot of photons. And this is then emitting things that we can detect on Earth. And that's how we can know that there was a tidal disruption event in that position. So we've done 24 neutrino follow-up campaigns, and we've actually found not one, but 2 different neutrino coincident TDEs. So yeah, we found AT2019 DSG on the left and AT2019 FDR on the right. And the probability of finding two bright TDEs by chance is 0.034%. So that's 3.4 sigma. So this is evidence that TDEs produce some of the high energy neutrinos, and theoretical modeling also supports this conclusion. And so I think I'm kind of out of time, and I'd like to leave some space for questions. I'd be really interested to hear from you. So I'm just going to leave up this summary slide. I already see there are a couple of comments in the chat. So yeah, thank you very much for listening. And yeah, were there any questions?